Hello, everyone. Welcome to this biomedical project presentation. And the topic is mesh size dependency on the tribological properties of PAA, which is polyacrylic acid, and agarose hydrogels. And I am Samsul Mahmood. I'm a graduate student of Mechanical Engineering Department, and my topic is related to tribology, which is friction. And I believe my lab mate Emily the other day mentioned a little bit about the friction, so I will add a little bit more to that and proceed with the main topic. So these are the outlines: background, significance, hydrogels, specific aims, related work, experimental approaches, and expected findings, and at the end, references. So the background. We all know that arthritis is considered as a serious health crisis. In recent survey data shows a good amount of people are suffering from arthritis, and CDC expects that 1 out of 4, or 54.5 million US adults, have some form of arthritis, and the number is likely to hit 78 million by the end of year 2040. And you can see at the uh, graph on the right side. Oh, and it is also known that osteoarthritis is generally tend to occur late in life and considered as a degenerative disorder. That means it cannot be cured. Pain is produced generally from damage, wear, and tear to the bone and cartilages. Osteoarthritis is not restricted to cartilage damage only, but can lead to the failure of the entire joint and can be very severe. And then comes the biolubrication. So since this work is related with the lubrication, I would want to add a little bit of detail into the biolubrication. And since this topic includes some technical details and the topic is relatively new, I would like to give a little bit of background and knowledge before I head to the main topic so the viewers can understand it properly. And for that, I maybe need an extra bit of time, and I would request to everyone to excuse me if that happens. So the biolubrication plays a vital role in assisting the sliding contacts in many organs in the body, not only in joints, but also the eye, gastrointestinal tracts, and red blood cells. And reduced lubrication can lead to friction and adhesion between the contact surfaces and lead to the surface wearing and cause pain, trauma, irritation, etc. One interesting thing is different part of the human body reacts differently to lubrication and relative sliding motions. For example, the joints need a friction coefficient which of an optimum uh, amount. It cannot be very high, it cannot be very low. If it becomes very low, then it will be analogous to a situation if someone tried to walk on a slippery surface and fell. If it is very higher friction, then it would cause wear and cause the arthritis even earlier in the ages. On the other hand, different regions of the human body needs lower coefficient of friction. For example, red blood cells, they need lower coefficient of friction than the joints. And now, continuing into the biolubrication, in the right-hand side, you can see the image of a synovial joint, and which is covered by the cartilages and synovial fluid. So when talking about it, we understand that the friction has static and dynamic friction. And static and dynamic friction are both present in joints. Human body uses various approaches and methods to decrease the friction in the joints, such as synovial fluid. Cartilage also helps in that manner. It works with the synovial fluid to reduce friction to stop bones from wearing away over time. Investigation is very important since the amount of the people having arthritis is increasing. That means that there's a possibility of higher amount of wear and friction. And to reduce it, we have to understand how it really works and how the biolubrication works, and the lubrication regimes works. So we'll talk about the lubrication regimes in the later sections. But we understand is that investigation is critically important. So now moving into the significance. So what happens when a human body walks or does daily activities. So the figure on the right hand side, uh, from there we can see that how many loading that human body exerts on a surface during normal motions. And we have to understand that the different joints have different loads and motions. So during walking phase, during a cycle time of 1.2 seconds, maximum load can reach about 1500 Newton when heel strikes the ground or toe is pushing up. And this is not a very small load. This is high load. And the behavior of the cartilages can be simulated by hydrogels in aqueous condition. Since the hydrogels can simulate the behavior of the cartilages, in recent time hydrogel has become a key thing for the researchers to look into and a study to understand more about the human joints and cartilages and their behavior under different types of loadings and lubrication. And the bottom figure, you can see the different types of motion. You can see when there is no motion, static friction is applicable. When it is sliding, there is a sliding friction, or you can call it dynamic friction. And during rolling, you can see the rolling friction. And you can always see this friction is a resistive force and always works in opposite to the working force. And one interesting thing is the static friction is always higher than the kinetic friction. And that leads to a joke that the hardest part is getting started. And it is actually true. And I realized it when I started working in this project. The hardest part was to get started. And I believe it probably was the same for the most of you guys. So now moving on to the next section, uh, why hydrogel? So likely I've already mentioned that the hydrogels can imitate the behavior of the cartilages. And to study about cartilages, we have to look into the hydrogels. So hydrogels are typically cross-linked polymer matrix with solvents such as water, tunable physiochemical characteristics, biocompatibility, and ultra-low friction. And these are its properties, and hydrogel exhibits change in volume for a small change in stimuli. So stimuli could be water, stimuli could be force, but the change is large. And let's look at the how hydrogel behaves underwater from this small video. All right, so I guess that is enough to give you a little bit of the understanding about what is exactly happening. And so you can see that the volume of the hydrogel changes with the increase of the uh, increase of the time, and it intakes water and swells. Now let's talk about the lubrication regimes and surface roughness. So in the right-hand side, you can see the typical strip-back curve and different lubrication regimes. The transition between the lubrication regimes basically depends on the surface roughness and the film thickness. And the film thickness is affected by the velocity, the viscosity, and the applied load. The boundary lubrication dominates in dense phase in human body, and it can be called the hydrostatic lubrication regimes that is applied when human body is standing. There are boundary lubrication, mixed lubrication, and hydrodynamic lubrication. And in most of the cases in human body have seen to exhibit to stay in mostly boundary lubrication and mixed lubrication. So let's talk about the significance more. So why surface roughness is important. So rough surface, when there's peaks and valleys in any type of surfaces, and when they come into contact, they cause friction, wears. Asperity plays a very vital role in biotribology. Chances of wear gets reduced by 7 order of magnitude if the boundary lubrication shifted from hydrodynamic lubrication. We have looked at the curve already. Boundary lubrication is where there is a little amount of film thickness. That means less amount of lubrication. but the friction can be reduced when there's a higher amount of lubrication and there is like higher amount of motion associated with the body. And to give you a little bit of idea how the surface roughness looks like, this is a surface topography of a 3D printed polymer specimen. And you can see that the surface roughness from the lowest point to highest point ranges from around -10 to +20. And this is not a very smooth surface since it's a 3D printed surface and it has some layers. But if we just look at one single layers, the figure on the top, you can see that still is not really smooth. It could be in the nanometer scale, but it's not really smooth. And there could be always microsparities, which affects the friction between the bodies. And now we're moving into our main topic, which is the specific aims for these projects. Aim 1 is studying the mesh size, dependency of the friction coefficient of hydrogel under varying normal load for a specified sliding speed. So for this, the hydrogel of variable mesh size will be synthesized and then tested on a custom pin-on-disc turbometer to investigate the load dependency on the coefficient of friction for a specific sliding velocity. We are keeping the sliding velocity fixed while changing the loading and also varying the mesh size to see the dependency of the hydrogel on it. The further analysis can be done to compare if the contact area follows the Hertz contact mechanics theory. And it will be done for the PAM, which is a polyacrylamide hydrogel. For the second aim, we'll still be looking at the effect on mesh size, but this time this will be for the polyacrylic acid PAA and agarose-based hydrogel. This time we'll be keeping the coefficient of friction, this time we'll be looking into the coefficient of friction and how it changes with the varying sliding speed. So for this time we'll be using a specific loading, but the sliding speed will be varied. So tribological properties of PA and agarose will be investigated similarly using custom microturbometer. Effect of mesh size on the coefficient of friction for varying sliding velocity will be tested. In situ imaging technique can be implemented to understand the friction behavior and different lubrication regimes as the velocity changes. So just let's look at some related works that what has been done in this topic so far. So from the top figure, we can see the coefficient of friction versus velocity for PAA. And you can see the velocity, sliding velocity is changing and the coefficient of friction is lower at the beginning, but with the increasing of the velocity for the PA and agarose, it increases, but then dramatically start to decreases. And this suggests two different lubrication regimes. For the first one, we can see the hydrodynamic lubrication, where the coefficient of friction increases. And for the later phase, when the coefficient of friction decreases with increasing velocity, we can see the mixed lubrication. Now let's see the effect of the normal loading. This is from another paper, friction behavior of the PAM hydrogel under wide range of speed and load. So normal force was varied from 0.1 millinewton to 20 millinewton. And you can see that the coefficient of friction is always lower for the higher loads. So this is the interesting phenomena since higher loads always contributes to the higher coefficient of friction for any other traditional material, but for these hydrogels, it's quite the opposite. Now let's look into the mesh size and talk a little bit about the mesh size. It takes a long time to talk about what really mesh size is, but I'm gonna touch a little bit on what is actually mesh size is and how it can be varied for these experimental approaches. So mesh size is known as the single parameter that controls dynamics of the existing polymer chains and elasticity of the hydrogels. That means hydrogel property is pretty much related with the mesh size. And also the control of the mesh size can be done during the synthesizing the hydrogel or during the polymerization phase by changing the monomers, by changing the cross-linkers and the water content, and also the solvents. For the PAM sample with the largest mesh size exhibited lower coefficient of friction and maintained such for a wide range of velocity. You can see it from the right hand side that the higher mesh size uh, had the lower coefficient of friction and it was similar. It stayed in the same range for 1 millimeter second velocity, and after that dramatic increase in the coefficient of friction can be seen. And coefficient of friction decreases with increased mesh size, which I have already talked about. And after transition sliding velocity, increasing coefficient of friction can be observed after increase of velocity. So it pretty much can be understood from the curve on the right hand side. And so experimental approaches and expected findings, what we are trying to find here. So we already know that PAM, PA, and agarose hydrogels has been tested, but not for the varying mesh sizes. But when the varying mesh sizes were tested for the PA and agarose, there was not any varying sliding velocity. So we'll look into those. For PAM, effect of mesh size on the varying load for a specific sliding velocity will be investigated. For PAA and agarose, mesh size dependency on the coefficient of friction for varying sliding velocity while keeping the normal load fixed will be investigated. Different lubrication regimes and its effects on coefficient of friction will be studied. In situ imaging techniques can be implemented using confocal microscope to better understand the sliding behavior of the hydrogels. And we can also look into the contact area and to verify to see if it follows the traditional Hartsian contact theory. These are the references, and that is all. And I probably took a longer time, and I'm sorry for that, but I really appreciate for the people for you guys to staying and listening to it. And I would definitely appreciate the feedbacks, valuable feedbacks from the peers. And if you have any questions, let me know. Thank you.